There we go. Okay. So I really like puzzles. Wasn't sure you knew that. But I really like puzzles. And that's part of the reason why I like recursion, because it allows us to take a look at puzzles in ways that you may not have been able to look at before. Now, as you may have watched the lecture video on this already, but if you haven't, it'd be a good time to check up on it because we're covering the Towers of Hanoi today. Also called the Towers of Brahma or Lucas's Tower. This is a fairly famous puzzle in general. Ooh, play puzzle. Play Towers of Hanoi. Okay, there we go. So this is a mathematical puzzle, mainly because there's mathematical solutions to it. But the objective is fairly straightforward. All right. And for those of you who, there we go. The objective is that you have a base like this guy. And you have 3 pegs, and you have some number of discs. I can grab them all from the bag. And that should do 3 discs for right now. The objective is to get, and I know this is hard to see, we'll take a look on the computer in a second. The objective is, hey, let's move all the discs from this side to this peg, to which you say, fine, that's easy. And we're done. But no, there are rules. First off, you can only move 1 disc at a time. Again, not so bad. You're like, okay, whatever. It's just stacks, right? You push and pop if you can only move 1 disc at a time, right? That's all the operations are. And now we see why it's a computer science problem. But that's not the only rule because, again, it's trivial. Not as trivial, but still trivial. So now I say, well, now we have an additional rule. You can't take a smaller disk and place them on top of another disk. So if we go to now this version, which you should be able to see over here, right? I can move this guy over here, but I can't drop this disk on top, right? I could move it here, but I can't just drop it on top. And so now it becomes a bit of a puzzle. How do I do? Now notice it says it has the minimum, it tells me the minimum moves over here. If I increase the disks, it tells me the minimum number of moves. And notice what's happening to the number of moves as I add a disk each time. With 6 disks, it was 63. With 5 disks, it was 31. With 7 disks, it's 127. So what's the relationship between the number of disks and how many steps it takes to get to a solution? What's happening each time I add a disk, relatively? 631 to 63 is approximately what? Yes? Yes, 2 to the n minus 1. That is the exact solution, where n is the number of disks. Effectively, adding a single disk doubles the amount of work you have to do. Let's go back to 3 disks over here. To do this, we drop 1 disk over here. Well, we can't drop, well, we think to ourselves, wait, I can't drop this over here because what we need to do is that we need to get this disk over to here, right? What I need to do in order to get this puzzle is that I have to get this bottom disk, okay, all the way over to here. In order to get the bottom disk over, or all the way over to here, to this last point, to the last peg, I need to get these top 2 disks out of the way and put them over here, right? In order to put the top 2 disks over here, I have to put the top disk over here, which means that, now it's out of the way. And so now I can move these top 2 disks on like so. And I'm done. Let's take a look at 4. This helps break it down even further. Okay, what I have to do is I have to get the bottom disk over here, right? Which means I have to move this pile of 3 over to here first. Okay, in order to move my pile of 3 here, I have to be able to get to this third disk, which means I have to move this pile of 2 over here. In order to move the pile of 2 over here, I have to move the top disk here, so I can put this here. So I can move this out of the way, and there. Now I can put the pile 2 on top of that disk. And now I've got a pile 3 over here. Now I can move this over here, which means I want to now move this pile 3 on top of here. So in order to do that, I actually have to do the counterintuitive move of moving that there. But it's not actually counterintuitive if you know the solution. And again, that's how that works. 15 moves to solve that. 5 disks, the strategy becomes very apparent when I describe it. In order to move, so what I have to do to move this pile 5 over is I have to get the bottom guy over to here, right? In order to get the bottom guy over to here, I have to move the pile of 4 to the middle, which means I have to move the pile 3 to the end, which means move the pile 2 over to here, which means I have to move 1 over here. Pile 3 goes there. Yeah, I know that seems weird, but I have to do that so I can get this over here. So now I have to move this 3. I have to get the bottom of this pile on top of here, which means move this out of the way over here, so I can get this guy over here. And now the pile of 2 is on top of 3, which is on top of the 4. Move this over here. Now I have to move a pile of 4 on top of here, which means I have to move the pile of 3 out of the way over here, which means I have to move the pile 2 over the way over here, which means I have to move the pile 1 over here. Pile 3. Pile of 4 now moves over to here. So the bottom disk moves here. Now I have to move the pile 3 back on top of that bottom disk. So pile 3. Let's see. Nope, I messed that up. Dropped it in the wrong place. There you go. I accidentally moved one more than I should have. So there you go. So now these things get get quite big, by the way. As you can see here, there's a giant one in Mexico City's Universal Museum. Yeah. So there's an iterative solution, but what we're interested in is a recursive solution. Which again, why is that all messed up today? That's normally not. Aha, because it's an SVG. So the way this normally works is that the idea here is that moving a pile of disks, a pile 4, can be broken down into moving a pile 3 out of the way, moving the bottom disk on, and then moving the pile 3 back onto that bottom disk. Make sense? So 4 means let's move 3 out of the way to the peg I don't want to go to. Move the bottom disk onto the peg that I want to, and then move the pile 3 on the end. Okay. Similarly, moving a pile of 2 goes over here. In order to move the pile 3 over here, I have to move the pile 2 over here, which breaks down to those steps. Each of these steps is basically recursively saying, okay, figuring out the entire puzzle is hard, so let's break it down into 3 steps. Move all the top disks out of the way, move the bottom disk, move the top disks back on. Okay. In terms of coding, let's go ahead and write some pseudocode for that. Okay, in order to do this, we have some function called move. And we have 3, let's see, we have 3 stacks or queues stacks or lists or whatever. So let's see, we've got disks 3, 2, 1, with 1 being on top, and then move from move n disks from source to destination, or we can say source to destination. Yeah, that's fine. Using auxiliary, the one we don't want. Right? And the way we do that is fairly simple. If n is greater than 1, is greater than or equal to 1, if there's a disk to be moved, right? Because it's recursive, we're going to need an end case. The end case is that if we're at 0 disks, don't do anything. So move n minus 1 disks from the source out of the way to our target. So out of the way to auxiliary, right? Notice that I've swapped, that I'm moving from the source to the auxiliary now, and destination will be the target over here. Move. Okay, and then what I need to do is I have to do, let's see, I have to push, yeah, I have to pop. So a dot pop, and not a dot pop, source dot pop, and then destination dot push. So pop it off of the source, put it onto the destination, right? And then what we do is we do another move. Okay, move from the n minus 1 disk that we had on auxiliary, move them to the destination, and the third disk is going to be our source. So the third peg is going to be our source. Make sense? So move here. So we move from n minus 1 from source to auxiliary to destination. Sorry, from source to auxiliary. So we take the top 3 disks. So we take the top disks, we move them into the middle peg. We move our final guy over to the end or wherever he's moving, and then we move the other 3 top on. Okay. So obviously, this is just pseudocode, right? This is just pseudocode. So we'd obviously need to add a little bit more. We'd have to add actually a bit more to get it working, right, in an actual programming language. So let's do that. Def. Let's add in the colon here, and I need to change this from push to append, I believe. And that should be a working Python program now. The thing about and let's go ahead and print A, B, C, sep equals new line. That just means that basically that instead of printing them out next to each other, I'm going to have them print out as new lines. So sep is equal to clutch n. And that should move 3 from A to C using B. Let's go ahead and see him run this. Let's go ahead, desktop towers.py and identified in Python. Let's see. I did want to run it. Come on. You can do it. Why is it not running? Jeez. Okay. Well, is it because? Okay. Obviously, give me 1 sec. It doesn't like the fact that I wasn't working in a folder previously. So let's see what I'm doing here now. All right, here's a Python file. Let's go ahead and run it. Trust the workspace. There we go. And there we go. Oh, is he greater than or equal to 1? I accidentally deleted the 1. And there we go. And print Let's print out an empty line over here as well. There we go. So we moved one over here, then we moved the 2 over here, then we moved the 1 back on, move the 3 over to the end, put the 1 out of the way so we can put the 2 on, and then we move the 1 over to here. So the thing about recursion, if you haven't felt it yet, is that it feels like it shouldn't work. That feels like the code is way too simple, and yet somehow it does work. Make sense? Your task today is to write a Towers of Hanoi solution in Python. Now, this is actually fairly trivial if you don't get tripped up, right? You make your stacks and the like. So where do students get tripped up? Well, it's this. It's the fact that I've got source, destination, target, and I've got A, B, and C. These are different things. A, B, and C are static variables, right? Whereas, and they're or globals in for Python. Whereas source, destination, auxiliary, those are your local variables. So you got to make sure that you can tell them apart, that you can handle them appropriately to write this. Okay. And again, I was just kind of going off of not memory, but yeah, kind of memory, because if I recall correctly, they do have that pseudocode like in here. But there are different types of towers. There's different mathematical solutions, graphical representations as it shows. There are solutions with 4 pegs. There are bicolor towers of Hanoi, where if you've got 2 towers of 2 different colors, but you need to that have the same rule, but what you want to do is you want to end up with them being in 2 separate stacks like this, which is that's a pretty nifty one. It's a pretty cool problem. I think it's there's even a drunken towers of Hanoi puzzle, which I find very fascinating on Project Euler, problem 497. So it's fairly up there, where basically you've got a quote unquote drunken mathematician, which is generally the facade that's needed for a puzzle to be done randomly. So the idea here is the mathematician, he knows how to do Towers of Hanoi, he can play it perfectly, but he cannot control where he is moving. So he will drop the discs on the appropriate pegs, but he cannot but it's a random dice move whether he moves left or right. And so the question here becomes, what is the expected number of moves that is needed for this puzzle to be solved, given the pegs are located in these locations on a path. And it does so by saying, hey, calculate the so if you've got if you've got 2 discs and 5 spaces, and your pegs are located on space 1, 3, and 5, it takes 60 approximate moves expected. And so it says, find the last 9 digits of this value to prove that you solved the puzzle, which is his own puzzle itself, which is pretty interesting. I remember working on it and making some progress on it last year, but then I had other stuff to do. But these kind of puzzles are fascinating to me. So what you'll want to do for today is, if you notice on Canvas that we have, I don't know why it's been asking me to log in every single time. Okay. If you go into our data structures class and you go to our modules, you'll note that we have we have an exercise here that says towers in class. I believe that gets sorted under quiz points, I think. Regardless, it's worth 10 points. So come up with a solution. Feel free to work with other people. It's not actually a quiz, it's just where the points are going. But feel free to work with other people to come up with a solution and then submit your solution there. I'll just briefly glance at it and give you credit for it. And then when you're done with it, you can work on it otherwise. Hi, Josh. Yes.
Sorry, Professor. I just want to clarify, what are we looking for, a Java solution?
Yes, a Java solution, implementing it in Java.
Okay, sorry. I thought you said Python earlier.
I did it in Python.
Got it. Yep.
I did it in Python because that resembles pseudocode and it emphasizes that it's a very, is that while it looks like it shouldn't work, that it does actually work.
Got it.
All right. Not recording.